For the next 20 minutes, I'm going to talk about some use cases of ONOS+Stratum, and then we will do the last hands-on exercise, which is a continuation of what you started in exercise 3. So I'm going to talk about 3 use cases that ONF is working on that are based on the capabilities provided by P4, P4 runtime, and Stratum together with ONOS. The first one is Trellis, and now we are able to provide a silicon-independent fabric using P4. The second one is the ability to offload very common functionality in residential network called BNG. And now we do this in SEBA, one other project inside ONF. And finally, how do we offload another functionality that's more common in mobile networks, which is the serving and packet gateway. I'll talk more about the different functions in a second. There is a error. This should be mcord. Yep. I thought I updated slides. Anyways, let's start with Trellis. So if you don't know Trellis, Trellis is a set of ONOS applications, actually a prominent example of ONOS application, which is in production today with Telecom US provider. It's a set of applications designed to provide connectivity inside a network topology arranged as a leaf-spine data center fabric. So the idea is to have, you can have multiple layers of like leaf and spines connect together, and Trellis takes care of providing connectivity as you would do in a traditional IP-based fabric. The only difference with traditional fabric is that this is all open source. It's based on white box switches. It was originally designed to work with Broadcom silicon, like Tomahawk, Trident, using the OF-DPA switch agent. It's based on open source software like ONOS, and the Trellis app itself are open source as well. It provides an extensive feature set, such as support for simple things like bridging, VLANs, PV4, and V6 routing, multicast, ability to integrate with external routers like BGP speakers, support for double VLAN tags like QNCube, pseudo-wires, and more. And as I said, it was initially designed to work with Broadcom silicon. What P4 made possible to us was to essentially support Trellis with different type of silicon, like P4 programmable silicon, without modifying the Trellis application itself. So this is what the ONOS architecture looks like. With this is a diagram actually of a network with ONOS on top and the Trellis application. So we have different applications like segment routing, providing connectivity inside the fabric using MPLS-based segment routing with the vRouter functionality, multicast. The idea is that these apps are able to control the network using the Flow Objective API. So for this reason, we say the Trellis applications are pipeline agnostic. And what we have in ONOS today is a driver for the OF-DPA Broadcom pipeline. Again, if you're not familiar with OF-DPA, you can think of OF-DPA as an open flow agent running on top of Broadcom switches, so running on top of the Broadcom SDK, exposing a very specific pipeline. And today, Trellis works with different silicon from Broadcom, like Qumran, Tomahawk, Trident 2. Thanks to P4, we were able to add support for other type of ASICs in Trellis, such as Barefoot Tofino, and we also demonstrated support for Mellanox Spectrum 1. So what we did, we wrote a new P4 program that's called fabricDeviceConfig. We packaged this P4 program in a pipeconf, so together with the behavior implementation you've been exposed in the previous exercise. And thanks to this, we are able to run Trellis also on top of the switches without changing the application. So we're running the same production-grade applications as before. We did a demo last year with this mixed fabric demo in which we had a topology with 10 switches. Half of them were based on OF-DPA, and half of them were using Stratum, in this case using the Barefoot Tofino ASICs. And this just to show how we were able to achieve interoperability inside the fabric, and also show evolution path from OpenFlow-based network using fixed function ASICs to P4 programmable one. So the idea is that you can use P4 first to replicate the same functionality that are provided by the fixed function switch. And once your network is entirely programmable, then you can start rolling out new features using P4. So thanks to the ONOS architecture and this idea of like having a flow objective API and the ability of like supporting different pipeline, we were able to achieve this interoperability. So talking about the fabric.P4, this P4 program, it's a P4 implementation of the Trellis reference pipeline. It is inspired by Broadcom OF-DPA. So it's a pipeline that might look familiar to you if you have any experience with, let's say, the Broadcom SDKs. But differently from that Broadcom pipeline, it's tailored to the Trellis needs, meaning there's fewer tables and it's easier to control from the control plane perspective. Again, the goal here was to bring more heterogeneity in Trellis with P4 capable silicon. And the cool thing, and I'll talk about this in a second, is that fabric.P4, since it abstracts a logical simplified pipeline on layer 2, layer 3, and MPLS features, it can work with both programmable and fixed function chips. So any switch pipeline can be mapped to fabric.P4, can be used with Trellis. And that's, for example, why we were able also to demonstrate support for this on Mellanox Spectrum 1, which is an example of fixed function ASIC. As I said before, one of the benefits of using P4 is that it makes the life of control plane developer easier. And that's because you can design your pipeline in a way that it makes sense from the control plane perspective. So in ONOS, we have this flow objective API, which is essentially a 3-stage logical pipeline. We have a filtering stage, forwarding stage, and a next stage. You can see the filtering stage is a table that matches on like the VLAN tag and the ingress port and decide to either allow the packet or drop it. You can see the forwarding stage is the implementation of routing tables, bridging tables, and finally the next stage is where we map this next ID to like routing actions or bridging actions or ECMP, multicast, etc. So given this API in mind, and given the fact that Trellis was already using this API, we wanted to come up with a solution that would allow us to use P4 and use silicon as quick as possible. So essentially, we designed fabric.P4 in a way that provides almost a one-to-one mapping between this logical pipeline and the tables in the P4 program. Now, one thing I want to mention is that I described this flow objective API in ONOS as an enabler of application portability. So the idea is that you can write applications that are portable across different pipelines. But as I said before, this API was introduced with OpenFlow 1.3 and to deal with the exploding heterogeneity of OpenFlow pipelines. And we quickly realized that even if it helps achieving the goal of like silicon independence, so again, the idea of like running the same applications on top of ASICs from different vendors, it's actually not that easy because mapping flow objective to hardware pipelines is pretty hard. And the reason it's very simple. Flow objective is a Java API. It's handler specified. It's written by developers that maybe don't know much about data plane pipelines, and it's ambiguous, and it's written in Java, which is really not a language to specify things like packet processing. So we really think that P4 is a better tool to actually specify logical pipeline. And we realized this by looking at the pipeliner implementation in ONOS. So on the very left, what you can see is the first implementation of Trellis running on Broadcom ASIC. So again, we have the Trellis applications. We have the flow objectives that are being pushed to the ONOS core. And then we have this layer called the pipeliner that maps this flow objective to the OF-DPA pipeline. And that's a very complex implementation. We did the same to support other switching ASICs. And again, we came up with very complex and hard to maintain pipeliner implementation. Because with fabric.P4 and programmable ASICs, we have the flexibility of arranging the pipeline in a way that is convenient to us. We were able to come up with a much simpler implementation of this pipeliner that is easier to maintain. But most importantly, since fabric.P4 abstracts capability that are common to many fixed function switches, I mean layer 2, layer 3, MPLS, things like that, it can work with both programmable and fixed function switches. And the good thing about P4 is that now that we have a pipeline that is formally specified using a language such P4, the effort of mapping this pipeline to different ASICs can be left to compilers or can be manual. But again, it's not dependent on an ambiguous specification of the API itself. Just to give you an example, on Wednesday, during the next-gen SDN track, there will be a talk that will describe how P4 compilers work for fixed function pipeline, and how these tools and P4 make it easier to generate these mapping layers, even for fixed function ASICs. To give an example, this is the line of codes used for the pipeliner implementation in ONOS for OF-DPA and fabric.P4. It's roughly 3 times more line of codes for F-DPA for pretty much the same capabilities. You might be asking, why do you need 2,000 line of codes for a one-to-one mapping? Well, Java is very verbose, let's put it this way. But again, the goal here is to show how P4 makes the life of control plane developers easier, because again, you just define those capabilities that you need in a way that is convenient for you. So the cool thing about this work, Trellis, is that once we have a pipeline and a control plane that for a fabric, we can extend this fabric with more advanced functionality. An example of this is BNG offloading. So if you're not familiar with the BNG, BNG stands for Broadband Network Gateway, and it's a fundamental piece of a residential access network. So in a residential access network, you usually have a residential gateway, which is the home gateway that's usually found in your house. We have, in the case of optical connectivity. Then we have an optical line termination, and then we have this BNG. So DLT has been already virtualized by ONF, thanks to a project called Volta. If you're not familiar with it, it's okay, you can learn more in the next days. But we still have this problem of the BNG, which is a very expensive box. It's has considerable weight on the market, and operators are eager to also virtualize this box to reduce CapEx and OpEx. This is a fundamental piece of a residential access pipeline, as it performs many functions related to subscriber termination, as it performs things like protocol-specific terminations like PPOE or Q&Q. This is where we do accounting. This is where we do QoS for both for the downstream direction of traffic, lawful intercept, tunnel relay, multicast routing. So how do we virtualize such a box? So the way ONF virtualized the first part of the pipeline comprising the OLT is with a project called SEBA. I will not spend much words on the details of the architecture, but the idea is that we can virtualize the same pipeline showed before using white box hardware, such as this OpenOLT from EdgeCore, white box switches, and open software controlling that. In this case, this Volta piece, together with the OpenOLT, is the way we were able to virtualize the OLT piece of the pipeline. But as you can see, the BNG is still external. So operators are interested in, again, virtualizing this piece. So we ask ourselves, how can we disaggregate it and embed in a SEBA pod? And the solution is very simple. We can actually disaggregate this box in 2 pieces, a user plane and a control plane, where the user plane is responsible for the packet processing intensive functionality, and the control plane is responsible indeed for the control functionality. So the idea for the user plane is to implement this function as part of the fabric of SEBA using P4 and merchant silicon, like silicon is available from vendors like Barefoot, Tofino, or Broadcom. For the control plane, the idea is to have an applications running on top of ONOS whenever possible, integrated with existing control planes. We don't want to re-implement things that already exist, such as an external, such as PPOE server or BGP speakers. This is what a disaggregated BNG looks like in the ONF plan. So we have the control plane and the user plane. The control plane is where we run functionalities related to, for example, subscriber authentication, addressing, routing, or PPE session discovery. And in this case, this picture at the bottom shows a diagram of the packet processing pipeline of the user plane for the two directions. So the upstream direction from the subscriber to the internet, and the downstream direction from the internet to the subscriber. We have different blocks that corresponds to, you can see that as the packet processing functions that the packets needs to go through. There are many different functions like classifications, policing, double VLAN termination, PPOE termination, lawful intercept, etc. What we are demonstrating today, and I encourage you to visit our demo in the next days, ONF Connect, is an implementation of this BNG-u, where the boxes with this black thick line are implemented using P4 on a barefoot Tofino ASIC running a line rate. The dotted boxes are still work in progress, and we also realized that although P4 is great, as of today, we cannot use P4 to solve, every possible problem. There are still things that it's hard to describe and implement using P4. One of these things is QoS, so the ability to define queues, schedulers, the ability to define scheduling policies. This is, at this point, left out of the P4 specification, and also is not implemented by most of the P4 hardware targets we're planning to use in this case. And that's why we're planning to use different chipset for these functionalities. So this is what the new SEBA architecture looks like. This is what we call SEBA 3.0. It's a work in progress. I've lighted in red what's new. So we have a P4 programmable Tofino-based switch instead of a Tomahawk-based one. We are using Stratum with a P4 program as the switch software stack instead of Broadcom OF-DPA. And now we have this BNGC application running on top of ONOS. The P4 program running on the switch is a version of fabric.P4 that already provides functionalities like routing and bridging and multicast, but has been extended with some BNG-specific tables, for example, to be able to process the PPPoE header. This is the demo we're showing at ONF Connect this year. We have a very simple setup. This is the traditional SEBA deployment, where we have an ONU, an optical line termination, a switch, and an upstream router. In this case, it's augmented with 3 new components. We have a subscriber that is running a PPPoE client. If you're not familiar with PPPoE, it's a protocol very common in residential networks. Not everyone is running PPPoE. Some operators in Europe do that. I think AT&T doesn't use that. Anyways, it's one of the protocols that you might need to support if you want to provide as an operator residential access. So we have a subscriber configured with a PPOE client. We have an external PPOE server. This is an unmodified server from open source project called RP-PPPoE. And we have an application called on top of ONOS called BNGC Relay. So the way we were able to disaggregate the BNG is it works this way. So the first thing that the PPOE client tries to do is to establish a session to actually access the internet. So it will start by exchanging some PPPoE control packets to establish a session, to authenticate the subscriber, and get an IP address. All these packets are intercepted by the P4 switch using packet ins, are sent to the BNGC relay that then relays these packets to the external PPOE server using packet out. What happens at the same time is that the BNGC relay is looking at the content of the PPOE packet to learn the subscriber session state. So in this case, we're learning the session ID, if the session was established or not, the IP address that the PPOE server assigned to the client. Once we learn all this information, both the Trellis application and the BNGC relay app program the switch to enable the PPOE termination, and also the Trellis application can install routing flows to route packets to the internet and back. So once the stable entry has been installed, the subscriber is connected to the internet, and all traffic is forwarded through the hardware fast path, so it's not going through the PPOE server. And the switch is performing termination. So the switches, in this case, receives packets that are tagged with 2 VLAN tags that are associated with the ONU and the OLT, and a PPOE header that identifies the session. We wrote a P4 program that is able to transform these packets, remove this header, and send it to the internet. For the downstream direction, we do the opposite. We receive untagged packets. We look at the destination IP address, and we have tables that then add the necessary headers before sending the packet to the OLT. Clearly, the benefit of this approach is, as Brian was mentioning in the introductory slide, was that when the idea of NFV came out, everyone was excited because of the benefit of virtualization, the ability to reduce CapEx and OpEx. But when you deal with high throughput applications, it becomes a bit hard to scale this type of VNF on a computing infrastructure. What we're doing here, we are disaggregating a BNG solution, taking advantage of merchant silicon. So the subscriber traffic termination is happening entirely on a switching ASIC, and it's running a line rate. So definitely we don't have a limit in terms of throughput. We have other limitations we need to deal with, and we need to come up with solutions as engineers, which relate to scalability in terms of like memory, how many subscribers can we support. If we need to support QoS, then we might need deep buffers. But this is definitely a start. Another example of VNF offloading is that of a serving at packet gateway. A serving at packet gateway, it's a box that performs very similar functions to a BNG, but for the mobile world. Essentially provide ways to terminate GTP tunnels. There are tunnels established by the base station to the serving and packet gateway, and are used to carry user traffic, subscriber traffic. So in this picture here, I'm showing the version of MCord, where MCord is an NFV-based mobile access platform developed by the ONF community. This is the version of MCord where all these VNFs are running in the computing infrastructure. So we have VNF like the SPGW-u and SPGW-c, and the MME and HSS, which are more related to control plane functionality. In this case, the packet processing functions are happening inside a server. So you can see packets are received by the switch. They leave the switch. They go through a server, which process functions like GTP tunnel termination, filtering, again, QoS, very similar to a BNG, and sends it back to the fabric to go to the internet. What we did, again, was to use P4 to implement the same functionality, but this time running on a switch. And to do this, we created a program called SPGW-u.P4. This is a very proof of concept implementation. It's around 300 lines of P4.16 code that, again, like the BNG case, is integrated with fabricDeviceConfig. The implementation is available online, so if you want to take a look, feel free. I'm not saying this is a fully fledged SPGW implementation, and right now, we didn't do any progress on that. At this stage, it's good enough to do some demonstration of end-to-end connectivity. And it supports functionality like GTP and cap-decap, filtering, charging functionality. There are important missing features, like, for example, these are features that are fundamental in mobile networks, like buffering of downlink packets during handovers, or again, QoS for downlink direction. And again, this is where P4 is not enough. For example, the buffering problem, the idea here is to have a box that is capable of like pausing and resuming flows while mobile users are moving from one base station to another. And the reason is that if the same box, the SP gateway, is doing a counting of packets, if it's counting the packets that it's sending to a given subscriber, if a packet is sent and at the same time the subscriber is moving from one base station to another and that packet is lost, then the subscriber might complain that accounting is inaccurate. So you need the ability to pause and resume flows. This is not something you can describe using P4. This idea of a programmable buffer that can hold packets for an arbitrary amount of time and release them is not something you can describe using P4. The same thing for QoS. So I guess what I'm trying to say here is that there is a number of things can be achieved with P4. That allows you to execute these functions on a chipset that is designed for packet processing, like a switching ASIC. But there are a number of challenges we need to face as a community, so that's why I encourage everyone to be involved in the work ONF is doing in this to also solve this problem. This picture shows the architecture with the integration with the control plane. So differently from the BNG case, in which we use an unmodified PPOE server, and we have an ONOS application that acts as a relay. In this case, we have the serving and packet gateway control plane that implements a standard API to talk with the SP gateway user plane component. In this case, we have an application running on top of ONOS that on the northbound implement the same 3GPP standard API. So the 3GPP calls, in this case, to create, modify, and delete subscriber tunnel termination are then translated by the application to P4 runtime entries. Okay, so that's what I have to say. What I have to say about use cases. Unless, do you have any questions or? Okay, if you don't have any questions, we can probably move on. On the last exercise, if exercise 3 felt easy, almost the 70% of you were able to complete it, I invite you to work on exercise 4, where you have to modify both P4 code and Java code and run some unit tests to finally enable IPv6 routing. So we said we want our topology to behave like a standard IPv6 fabric, but the implementation we provided you with is broken, and your task is to fix it. So the steps of the exercise are to first debug the issue, but don't worry, you're going to find some step-by-step instructions. You will find that the issue can be fixed by updating the P4 program. But since you are modifying the P4 implementation, we want to make sure you're not, first of all, you're implementing the new features in the right way, and you're not broken any other existing functionality. So that's why you will also be asked to run some PTF tests, where PTF stands for Packet Test Framework. Essentially a framework to do data plane unit testing for P4 programs. Finally, you'll be asked to apply some simple modifications to the ONOS app application, and then you should be able to do a connectivity test between hosts attached on different IPv6 subnets. In this case, you should be able to ping hosts attached to different leaves and packets being forwarded across the spines. So I mentioned this packet test framework. Again, it's a way to do data plane unit testing for P4. It's a Python-based framework. It's similar to OpenFlow test, if you ever work with that, but the difference is that this is independent of the runtime control protocol used to populate table entries. It's a framework that essentially allows to take a switch, like a P4 runtime, a Stratum-enabled switch in this case, provide a runtime configuration in terms of like pipeline and table entry, send an input packet, and verify the output. That's why you can write unit test for packet-based unit test for P4. Now, what does it mean to have an IPv6 fabric? Again, we want our fabric to behave like a standard IPv6 fabric. So these are the functionalities that should be supported by our switches. So we have leaf switches and spine switches. Leaf switches should behave as a traditional router, meaning that you have a device with ports. Each port can be associated with an interface with an IP configuration. So you should be able to logically assign IP addresses and subnets to the interface of our router. host attached to the leafs should be configured with the gateway IPv6 address, the one you assign to the leaf. This way, the host should be able to route packets through its gateway, which is the leaf switch in this case. Because of this, then hosts should be able to resolve the MAC address of their gateway, meaning that the leaf switch should be able to reply to NDP neighbor solicitation messages sent by the host. Again, when you want to route a packet to the internet, the first thing you need to do is resolve the MAC address of your gateway. And if in IPv4 we use ARP, in the case of IPv6, we're going to use NDP. So the first thing the host does is send an NDP neighbor solicitation message to the switch, and we expect the switch to reply with its own MAC address. Finally, not all packets need to be routed by the leaf switch. We've seen before that some packets are forwarded using the bridging table, so we need to distinguish between packets that needs to be bridged and packets that needs to be routed. If you already looked at that part of the P4 program in exercise 1 that deals with IPv6 routing, you might have noticed this table called MyStation table that matches on the packet destination MAC address. In this case, we expect to find a MAC address that is assigned to the switch. Finally, the switch provides a routing table that maps IPv6 prefixes to next stop. And we also want to support ECMP, meaning the ability of load balancing traffic to links across the spines. I know it sounds a lot. Fortunately, your task is to modify one little thing of this list. I'm not telling you what. You'll find out during the debugging session. Since we are running what it should like a traditional IPv6 router, we also need to provide some IPv6 related configuration to our fabric. So if you look at the netcfg.json file you pushed before, you will notice that there is a section of this configuration related to each device where we specify the so-called MyStation MAC address. So this is the MAC address that is associated to the switch. And that's the MAC address that the switch will provision to the MyStation table. So when a packet is received with this destination MAC address, then the switch will process the packet through the routing table. And there is also a flag to say if the switch has to be used as a spine or as a leaf. There is also another part of the configuration that specify the IPv6 configuration associated with the switch interfaces. In this case, we are specifying that for device leaf1 port 3, we want an interface configuration with this IP address and subnet. Yeah, maybe I can repeat this for the recording. So one of the simplification we have in our fabric is that usually in a traditional router, you might have different MAC addresses associated with the different interfaces. In here, to simplify things, we only have one MAC address for the whole switch. So all packets coming out of the switch will have the source MAC address, and the switch will only route packets with destination MAC address, this one. So just to recap how IPv6 routing work, assuming we have this topology, one host, two routers, or switches in this case, Stratum switches, and a host at the other end. Clearly, host 1 will send a packet with MAC source its own, and MAC destination the one of the router. And router 1 will modify the Ethernet source and the Ethernet destination to use the one of router 2, and so on, finally routing the packets to host 2. So the question is, how does host 1 learn about the MAC address of router 1? Well, we use this NDP protocol. So in host 1, we know we already have a gateway configuration. So host 1 knows that to route packets to the internet, he has to send these packets to the router with this IP address. And to do that, he needs to learn the MAC address of this guy. So what host 1 will do, will send first a NDP neighbor solicitation message or router solicitation, depending which mode you're using, asking who has the MAC address of that gateway IP address. And here we expect the router to reply with its own MAC address. So the question you will try to answer during exercise 4 is how to generate these NDP replies from the switch. So once this NDP thing is done and hosts have learned the MAC address of their leaf, we have two types of routing. We have same leaf routing, where the switch routes packet to host connected to the same leaf. But we also have ECMP routing, meaning that packets are routed across the spines to be delivered to the other leaf. In this case, since we're using ECMP, if we have multiple flows, we should expect to see flows being hashed to the two paths. And during the exercise, there's a step that allows you to visualize this phenomenon. Like in the previous exercise, where we had an application component that was controlling the bridging part, we are already providing you with a component that implements our router control plane. It's a very simple implementation that listens for device and topology events, and for each device, provision all the necessary flow rules and groups to provide routing. So for example, this is the component that installs a flow rules that matches on the MyStation MAC that is defined in the netcfg file to enable the routing table. This is the component that installs flow rules to route packets attached to the attached host, and also install the flow rules to route packets to distant leaves. So the difference is that in the first case, we match on the /128 address of the host, and the second case, we match on a prefix that is derived by the interface configuration of all the switches in the network. This component is also responsible of creating the ECMP groups to hash traffic to the different spines. Now, if you want, you can take a look at implementation or take it for granted. The task, your task is actually to fix a different component. Okay, this concludes the exercise overview. If you have any question, I'm happy to answer now. Otherwise, you can start working on the exercise. And we have until 5, so it's roughly 50 minutes from now.